A very important aspect for computer science was how information could be represented that a machine or automaton can deal with it. So, information like this film which you're watching now, or signals from far away, from billions of light years away, like here from radio stars or quasars, must be converted into a format which can be used to process them and to analyze them. But not only with that, you need a special method or a special technique also for controlling such a telescope. This telescope is nothing more than a huge robot which is controlled by different computers, and everything, each state is represented in a so-called binary way. So each LED, what you see here, represents a state which gives you information about what the telescope is doing. And therefore our first lesson will touch this aspect, the binary world. So please follow me. Welcome to the first section, binary world. So today we will talk about things like what is a computer, what is required for calculation, and how can we represent numbers so that a computer can understand them. And then I will give you a short introduction about which problems appear if you represent numbers in the way a computer does. So let's have a look into the next things which you find everywhere in the internet. So what is a computer? How would you explain a computer? If you search Wikipedia, you will find something like a computer is a general purpose device that can be programmed. So it's quite important, this programming aspect, which can be programmed to carry out a set of arithmetic and logic operations. So arithmetic and logic operations are quite important. So calculation, for example. If you search other encyclopedias, you will find things like that. Computers are programmable calculation machines to process, calculate operations on the basis of mechanical, electrical, or electronical devices. And quite important is that computer processes data to perform mathematical, converting, transferring, or saving operations. So the data aspect is also a quite important thing for that. If you want to do that, if you want to do calculations, which is quite an important aspect, so we need something to represent the numbers which can be calculated. Therefore, what do you need? You need a representation of a number. You need a set of rules which operations are allowed, and then you need a possibility to use them in, let's say, an electronic device to do this calculation. Let's first of all focus on the suitable representation for a computer. We all know the base 10 system. So we have 10 fingers. These 10 fingers are, for us, the known way to calculate. So you have 1 plus 2 is 3. You have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you have a separation between the representation of a number and the value of a number. So what you see here is the representation of a number, and as we are so used to handle or to deal with this base 10 system, we automatically see the value of this. So it's 23,045. But in principle, this is just the representation. The representation is how the numbers, for example, these numbers, these signs, are arranged so that you represent it in a readable form. The real value of this number comes from a calculation. So you have something like a positional system. So each position here has a specific value. So this is the position 1, this is the position 10, this is the position with a value 100, and this is the position with a value 1000, and so on. So if you want to convert this representation to a value, you have to do the following. You have to take this number and multiply it with 1. And then you have to take this number and multiply it with 10. And then you take the result and add it to this result. So, for example, 5 plus 40 plus 0 plus 3000, and so on. So you have the base 10 system, so it means you have 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on. And to get the value out of this representation, you have to sum up all single values according to the position to get the final value. As I said, we used to deal with this stuff, and therefore it's quite simple. So you just look at it and you directly see it's 23,045. But a computer would convert this representation of signs, of characters, to a value. Important is that in this part here, you have always a unique representation, and it also includes the 0. So if everything is 0, you have a 0 representation. And you have, as I said, a method to operate with them. So for example, the most important operation is the plus. And the plus gives you also possibility to calculate the multiplication, because multiplications are always a sequence of pluses. So how do we do this? We have the positions which give us the value, and if you reach a value which is greater than what we can represent here, we do a carryover. So 5 plus 9 is 14. We take the 4, because this can be represented here, and we carry over the 1. And then we calculate 4 plus 9 plus 1, and then we have again 14. We take the 4 and we carry over the 1. So this is how we do the addition, for example. We can create representations, or we can create operation methods for all of the operations. And what is also possible, or easily possible in this way, if we have this valued system, we can compare the numbers quite easily. So if we take here a big number and compare it to a smaller number, it's quite easy. We just have to compare the length, and then we compare each value. So if the first, if there are more numbers in the higher region, then we automatically know, okay, this must be bigger. So if we would compare this, if this number compared to this number, one is bigger or greater, then we automatically know that this one with a greater number at the position is then the greater number. So we have a possibility to logically compare things. And what else? We have a possibility to represent plus and minus numbers. So if we can do calculations, so if we can subtract numbers, we also can do a representation of minus numbers. And we have a possibility of fractions. So here we have numbers in front of the decimal dot, and we have numbers in the fractional region. And how is the calculation done here? It's the same like in front of this dot. Here we calculate the value which is represented here times 10 to the power of 0, for example. And in this direction, you always multiply with 10 to the power of -1, -2, -3, and so on, so that we shift it to the right value order. If you want to do this in a way that a computer can do it, we have to represent all of these possibilities available for the base 10 system also to a possibility for a computer system. So for a computer system, in base case we have two states. We have turn the light on or turn the light off. So switch on, switch off. And this is a very easy way because it can also be represented easily, for example, with holes or sticks on a punch card. So therefore, two states are much easier to represent in electronic systems or in mechanical systems than these 10 states, where you have to define the levels and have to identify the levels. Especially if you do communication, it's quite difficult, because if you do a communication and you send bits or you send single of these elements, and you have some influences on your line so that it's a little bit washed out, that you don't see the signal clearly anymore, then it's quite difficult to separate here. Here, it's in most cases quite easy to identify, is it on or off. So therefore, the same as with the base 10 system, we have to represent the same things. So now we have just two values, 0 and 1. And we can represent all numbers with these two values. In this case, again, we have a separation between representation and value. So these are two characters, two signs. And these two signs can be converted to a value which is represented with this number. So for example, as we are now in the base 2 system, we just have two states, and the position gives us again the value. In this case, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 3, 4, 5, 6, and so on. So it means this is the value 1, this is the value 2, this is the value 4, 8, 16, 32, 128, and so on. So therefore you have always a multiplication by 2 from each value position to the next one. And what you also have is now the information why in computer science everything is based on such a base 2 system. So if you buy memory, you get something like 256, or you get 512, or you get 1024, sorry, and so on. So therefore it's quite fixed to these numbers. And how you can convert this again, you take the representation, you multiply it by the value for its position, and then you sum all of these things up. So if you have this here, you take 1 times 1 and you will get 1. You take 1 times 2, you will get 2. So 1 plus 2 is 3. 0 times 4, 0 times 8, 1 times 16. So you have 16 plus 2 plus 1, and so on. And at the end, if you sum all of these up, you will get here the number. So in this case, 211. So you can represent all possibilities with such a table, where you have all possibilities aligned here. And this table can be created quite simple. And this I want to show you. So it's quite simple to create such a truth table. You just start with the position 1, and then you just toggle the bit 1 by 1. And then you continue with position 2, and you toggle each second time. So that you have the sequence 0011, 0011, 0011. Then you continue at the position 3, which is 4 in value. And then you just repeat 4 times the same value. And this automatically generates all possibilities. So if you have this table, then you have here the 0 in decimal, the 1, the 2, the 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Given by 1 plus nothing, or 1 times 2 plus nothing, or 3 is 1 times 1 plus 1 times 2 plus 0, or 4 is 1 times 4, or 5 is 1 times 1 plus 1 times 4 plus 0, and so on. So what you automatically get is a combination of all possibilities. If you have just one bit, you have 2 possibilities. If you have 2 bits, you have 4 possibilities. If you have 3 bits, you have 8 possibilities. And if you would have the next position 4, which is 8, you would have 16 possibilities. So you see, it's quite simple to create such a table, which converts the binary numbers to decimal numbers. If we continue, then you should know that usually in the binary field you combine 8 of these single valued positions to one number. So one position is called bit, and 8 of them is 1 byte. So usually you have then combinations of 1 byte, 2 bytes, 4 bytes, 8 bytes, and so on. And therefore this setup of computer types is defined. So having such a nice method to represent the numbers with holes or pins or just states up and low, you can represent all of the things on punch cards or on different wooden boards or whatever. So it means if you have a hole or no hole, then you can set the number which you want. And it is still used here, for example, for car wash systems, so that you have the special service as a binary code on such a small piece of plastic. And the number of holes define if the state is set or not. What you also should know is that not only the binary system is relevant for the computer science part, also octal system, for example, with a base 8, or hexadecimal with a base 16 is relevant. This is called hexadecimal, and you will find often numbers which are defined in hexadecimal, because it's quite easy to convert between hexadecimal and the dual or binary system. So you have seen how easy it is to convert from a binary number to a decimal number. The vice versa conversion is a little bit different. So what you do is you take the number in decimal representation and you always divide by 2. So I can show you this in another example. In the truth table, you already thought how it is to convert a binary number to a decimal number. So let's do it again. For example, we have the number 1, 0, 1, 0, 1, 0, 1. And we always fill up to the next byte, so 8 bits with zeros. So these are 8 bits. And if you write the values, so you have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, 5, 6, 7, or in decimal numbers, complete 1, 2, 4, 8, 16, 32, 64, 128. So here is always a multiplication by 2. Then you can use these values to calculate the decimal number. You always take the positions where 1 is written and you write the decimal replacement: 1, 4, 16, 64. And you sum it up, plus, plus, plus. And what you get is 85 in decimal. So if we convert it back to binary, then we just use the 85 decimal and we now divide it by 2. So you get 42 and you will get a rest. And the rest is the binary number. So in this case, 1, it's an integer division, so you have no fractions. And you always take the next decimal number and divide it by 2. So 21, rest 0. 21 is 10, rest 1. 10 divided by 2 is 5, rest 0. 5 divided by 2 is 2, rest 1. And 2 divided by 2 is 1, rest 0. And 1 divided by 2 is 0, rest 1. And then you read it from here. So this is the lowest bit. So we have 1, 0, 1, 0, 1, 0, 1, and you fill it up with zeros so that you have the binary number again. And therefore, you can also calculate the maximum number, which can be represented in a binary field. So this means for 8 bits, you set everything to 1. And if you calculate this, then you will find out that you can represent with these 8 bits a decimal number, a maximal decimal number of 255. So you can also calculate this if you set this all to 0 and then the next to 1, and then you subtract 1 so that you also get this maximum number. So you can represent with this integer number from 0 to 255. And therefore you have these integer representations also available in data types. So all usual programming languages offer these data types. A data type for 1 byte, which is character or char, 2 bytes, which is short, 4 bytes, which is integer, and in 32-bit systems, operating systems, also long, or 8 bytes, which is long, or in 64-byte systems, only the long. So there is a small difference between the two different operating systems, 32-bit systems and 64-bit systems, so that they represent the long type in a different way, which also leads sometimes to problems in programming. Okay, what else do we need? If you have this number, there is no definition in which order you watch this. So let's go one step back. So it matters if you read it from this. So if the lowest value is here, or if the lowest value is here. So it's the so-called least significant bit or byte. So you have then two things which you have to think about. So first of all, this here, which is this least significant bit and most significant bit. Usually I use this representation so that the least significant bit is on the right side of this number, but there are also systems where it is exactly vice versa. And then it's also important, if you have a sequence of bytes, that it is also interesting if the first byte is here or the first byte is here. This is called big endian or little endian. So it's quite important if you read a number, if you see such a binary number, if you have big endian or little endian, and where the least significant bit is arranged. So now we have a method to represent numbers. The next step is how to calculate with these binary numbers, and this is the same thing like with the normal decimal numbers. So with the normal decimal numbers, you take each number and always use one of these columns which represent one value. So you have this value plus this value is this, and if you reach a number which is greater than what can be represented here, then you have this carryover. So you have here 1 plus 0, which is 1. You have no carryover. Then you have 1 plus 1, which is 1, 0, which means 1 plus 1 is 2, and 2 cannot be represented with 1 bit, and therefore you have 0 and 1 carryover. So then you have 1 plus 1 plus 1, which is 1, 1. So you have 1 here and a carryover of 1, and then you have 1 plus 0. So you can do the addition, and if you can do the addition, you can also do the multiplication, because several times of addition you have a multiplication. And exactly the same way like with the base 10 system, you can compare the numbers just according to the positions. So if you have a number which has more valued positions than the other, then you know it's bigger. If you have this comparison, you always compare this number with this number, and then you see which number is greater if the position is filled or not. So exactly the same like with the base 10 system with the decimal system. So what else do we have? If you do these calculations and if you use just bytes, then you have the situation that it might be that the number cannot be represented anymore. So it means that, for example, a number flows out here. So you have 1 plus 1 is 0, 1, or 1, 0. You have carry 1, and then so on and so on and so on. And that means that if you have just one byte, 1, 1, 1, 1, 1, 1, 1, 1, so filled completely with ones plus 1 will result in 0. So 0 is not the correct number in decimal because it would be 256. So it would be required that you have one bit more than what you have at the moment. And therefore, these are critical errors. So they are very famous samples where such overflows lead to really catastrophic situations. For example, Ariane 5 rocket crash was one of these situations. So there was a wrong type used. So they used short instead of integer, for example. And then it happened that you had an overflow in the acceleration parameters or whatever, and then you got something like this. So this is a really critical situation. So what do we else need? We need the representation of negative numbers. So it's easy to do that because you can only send in an additional bit. So you use only 7 bits for the real value, and you take the first one for the sign. So you have 0, which is plus, and you have 1, which represents the sign minus. The problem is here. So if you have the 0 with sign and the 0 without sign, you would have 2 zeros, a plus 0 and a minus 0. So to avoid that, you can use a trick which gives you a possibility to have just 1 0. And this is called the tooth complement. The tooth complement is shown here. So what you do is you toggle completely all bits, and then you do the same what you do upside, you do downside here. So you toggle always each bit here, you toggle each second, each fourth or each fourth bit sequence, and so on. So that at the minus range you have this setup, and on the plus range you have this setup. How can you calculate this tooth complement? Here are 2 samples to calculate the tooth complement, but I want to show you this with another sample exercise. Let's train the conversion to the tooth complement, which represents negative numbers. So method 1 is the method where you subtract the number which you want to convert to a negative number from 256. So let's say we want to produce minus 8. So what you do is you convert it in this way. You subtract the 8 from the 256. So you get 248 in decimal. Then you convert this to binary. So 248 divided by 2 equal 142 rest 0, 142 divided, and so on. So what you will get at the end is this number, which is the 2's complement for -8. Method 2 is you convert the number, the decimal number, to a binary number. In this case, it's quite simple because 8 is already one position in the binary number. So you have 1, 2, 4, 8. So the converted number looks like this. And then you toggle or invert each bit. So if you have a 0, it will become 1. And if you have 1, it will become 0. And then you sum 1. So you make +1, which means 1 plus 1 is 0. Carry over 1, 1 plus 1 is 0. Carry over 1, 1 plus 1 is 0. Carry over 1, 1 plus 0 is 1. 0 plus 1 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 is 1. So this is again the binary number in 2's complement. Let's have a look how it is in the truth table. So you have 0, 0, 0, 0, 0, 0, 0, 0, which is 0 in decimal. And -1 is all bits to 1. So it's -1. And then you do nothing else than what you did in the positive range. You toggle. In the first place or the first value, you always toggle once. In the second one, you toggle at each second. In the third, you toggle at each fourth. And in the fourth, you toggle at each eighth. So what you have here is -2, -3, -4, -5, -6, -7, -8. So you see, it's quite simple to convert to the 2's complement. The nice thing, if you have this, you can now use it for a simple calculation of a subtraction, because you now can use this 2's complement and you only have to do additions if you want to do a subtraction. So what does it mean? If you, for example, want to subtract the 2 from the 10, then you can also do an addition where you add -2 to 10. And if you have this 2's complement, then you just do the addition and you automatically get the correct number here for 1 byte. So another example can be shown here. For example, if you want to add -4 and -3, then you have these two numbers in 2's complement. You sum them up and you will get -7. You don't take care on this carryover part because you just focus on the 1 byte. So therefore, if you have these two techniques, the binary representation and the 2's complement, you can do the addition, the multiplication, which is several additions, the subtractions, and also divisions, because divisions are several, subtractions. It's a little bit more than that, but in principle you can get an idea of that. If you go back to the decimal system, we also had fractional numbers, so fractions, parts of a number, which were represented, for example, with a dot. So 23.4. So now we need a technique or a method to also represent these numbers in our binary system. First of all, we already know we spend 1 bit for the sign. So we have plus is 0, 1 is 1, and we have 1 bit which represents the sign. We also know that everything what is in front of this dot can be represented like a normal binary integer number. So what we do is we divide by 2, and then we get a binary representation. And we also know that everything what is behind here can be represented with 10 to the power of -1, -2, -3. So what we can do, it's something like multiplying by 2. So we use this, we take the 0.4 and multiply it by 2. And if we reach a state where we come to a position which is in front of the decimal dot, then we subtract 1. So if you do this, we have 0.4 times 2 is 0.8. We don't have to subtract something. Then we have 0.8 times 2 is 0.6. And from 0.6 we have to subtract 1. And then we have to use 0.6 times 2, which is subtraction of 1. And therefore, if we read it in this way, we will get a binary representation for the fractional part. And if we use the sign, the part in front of the dot, and the part behind the dot, we have a first representation of a fractional number. To simplify the usage of that, we do a little bit more steps. So we do a normalization. So we shift everything to a situation where we only have one dot something. So each shift means it's division, and therefore we have to multiply here 2 to the power of something. So in the first setup we multiply 1, in the next setup we multiply 2, 4, and so on. So if we normalize this, we'll get this setup, so 1.01 and so on, multiplied with the power of 4. And then we just use this, because we don't have to think about this 1, because all numbers will have the 1 here. So we use this, which is called Mantissa. And then we have to remember this exponent. And this exponent is represented in a so-called biased way, so that it is simplified for the use. We use the tooth complement because it can happen that we need minus representations in the exponent, and we do a bias with 127. Why? I will show on the next slide. So the final number looks like this. So you have a sign bit, then you have the Mantissa, and you have you have the sign bit, then you have the exponent, and then you have the Mantissa. Why it's in this way arranged? The exponent defines the size of the number, so you can do the comparison of the of numbers by just watching the bit order again. So it's like comparing the normal integer numbers. So you look onto each position and can directly say which number is greater than that. This is defined in the IEEE 754 standard or notation, and therefore this is the floating point notation. I want to come back to this exponential biased representation. So why it is used like that? You need a sign because you can have positive and negative exponents. Therefore, you don't want to use or you don't want to lose a bit in the case like we had with a -0 and +0. So we use the tooth complement. And then there's a trick which shifts all numbers to the positive range. So if you bias it with the decimal number 127, it's something like shifting everything in a positive range. And therefore, you have then an integer number which you can directly compare. You lose a range of numbers because now you can just represent 128 different states, including the 0. But that's enough for the exponent, and therefore you always have to calculate a bias to the exponent to get the real floating point number. But going back to this representation, with this trick you can directly compare these whole numbers according to an integer comparison. This is why it's used like that. Here's an overview. So what you have is the sign bit, the mantissa, and the exponent, and the representation is done in a way that the exponent is first and the mantissa is in the back bytes. A consequence of this is that you lose information. You have only a limited number of bits for the mantissa, and you have a limited number for the exponent. And therefore, you cannot represent all numbers. In integer numbers, you have a minimum number and a maximum number. Here you have also a minimum number and a maximum number. But because of the setup, you have also a minimum number or a minimum distance between two floating point numbers. So this is the minimal representable number or addition value which you can use between two floating point numbers. So this is called EPS, and therefore this EPS leads to some problems. So it is in principle, what you see here is in principle just an approximation of a real number. So the set of floating point numbers in binary representation is a finite subset of all floating point numbers in the rational domain. So what do we have? We have something like a finite arithmetic, and this can lead to problems if you have iterative processes, because you always have to cut off somewhere. You always lose information in the last bits, and therefore it can happen that it propagates to relevant positions. Nevertheless, you have different ways to or different types which are offered by the computer programming languages. So you have a floating point based on 4 bytes, which I showed you before. It's called float. Then you have 8 bytes. It's called double. So this is the usual representation, double precision calculation. And in 64-bit systems, you can also have a 60 bytes long double type. So this helps you a lot to improve iterative calculations, but it does not solve the problem completely. Coming back to these other data types, I want to show you just that it's quite similar to what you know from the binary system and the hexadecimal system. So for the octal system or the hexadecimal system, you have, for octal system, you have 8 numbers or 8 signs which represent it. You have again a system where each position gives a special value. So you have the signs, the representation, and the signs, and the real value. And the same is here for the hexadecimal system. The hexadecimal system has 16 values from 0 to 9, and 10 is A, 11 is B, 12 is C, 13 is D, and so on. So 15 is F. So if we have D3, it means this is the representation in hexadecimal system, where you have here the 13 and here the 3. I mentioned that there might be some problems in dealing with numbers which come from the numeric field. So numerics is a very important discipline. I just want to touch it with one small sample, which shows you that not everything what a computer calculates is automatically true. And the problem comes out of this floating point situation, that you always lose information because you have a limited world of bytes in your computer. What I can show you is that if you normalize everything, there might be a number where you lose information. So if you convert, or if you sum up and you bring it to a normalized situation, it can happen that you lose information. So especially big numbers and very small numbers, if you add them together, you will lose the small number because it will not appear, because it cut away in the big number. And this is called absorption. There are other things which can happen. So you can have the cancellation. So it means a subtraction of numbers with equal dimensions produce a wrong result. So it might be 0, for example, even if there is a distance between these two numbers. Then the absorption situation, what I showed you before. So if you have a big number and you add it to a small number, you will have the situation that the small number will disappear. So there's no effect. Then you can have a so-called underflow. Numbers lower than minimal presentable floating point numbers become 0. So they're all very related to each other. The problem is, if you have this situation, you will lead or you can come into situations where some mathematical laws are not true anymore. So the associative law might be wrong, and also the distributive law might be wrong if you deal with numeric. So it can happen that a solution can be found for equations which should not have a solution. So for not solvable equations, you might find a solution because of these truncation situations. Usually you have also problems, for example, if you convert a decimal number into a binary number. The problem here is that it's only a subset. So not all real numbers can be represented in the binary domain. And therefore, the conversion might lead to inaccuracies. And then you have the starting problem. Because if you start an iteration with the wrong number, the error can propagate quite much. So, for example, this is also written here, a representation problem of simple decimal numbers, so that you have something like this number here. So it's 0.0999 is almost 0.1, but it's not the same in real math. Okay? And I want to show you the problem with the so-called deterministic chaos, which comes out of iterative calculation. So chaos, you all know chaos, not only in your house, but also in math. So a chaotical system is you have a starting point, and after some iterations you reach an endpoint which you cannot calculate. If you start at the same situation, you will come to another chaotic endpoint. And in this deterministic chaos, you cannot calculate what happens, but if you start with the same start point, it will end up in the same result. So therefore, I can show you a situation like this. And before I do that, I want to show you also that between different operating systems and different representations there, you will find different limitations. So here for the Debian Linux, and here for the Windows system. So you see some different limits. So computer programs which run on different machines might lead to different results. So if we use the program only on one computer system, we avoid this starting problem in any case. The starting problem coming out of the operating system. We cannot avoid the starting problem coming out of the conversion between decimal and binary representation. But I can show you what happens if you do iterative calculations. So the idea comes from such a simulation. It's the Lorentz experiment, and he wanted to calculate weather models with calculators, with simple calculators. And at the days of this experiment, 1956, calculators had the possibility of 6 or 3 places after the floating point, and therefore they reached this situation that the error propagated to a position which were interesting happened quite early. And he did these simulations and found out that there is a really big effect in long-term forecasts, so that it is not possible to do this with these machines. So you can now say, okay, 1956, a long time ago. So let's have a look what happens now, because with double precision or something like that, it will not happen. So for this, I use a very simple iterative calculation. So you calculate the next step with the previous step. Why this calculation? This is the Lorentz Verhalts logistic model. You can use this for the calculation of maybe the population in a petri dish, or the population of people in a special country. It's not the best formula, so it should not be a very scientific approach. It should just show you what happens if you use a previous calculated result for the next one. So let's have a look. So these are the first steps, and you can say, okay, we have a lot of points, a lot of values behind the floating point. So why do I have to care on it? So let's do. Already after 4 steps, you have the situation that you lose information. So in this case, we are just interested in the 2 places after the dot, which means the percentage values, and therefore we can say, okay, we are so far away from these really relevant positions that who matters. But there is a big propagation, and I did it with a C program here. So you see what I did. I use float, and I use the representation in decimal, in double. So, and then we do the same calculation. If you watch these 2 lines here, it's exactly the same calculation. You can identify the float representation here with this F, and the double representation with a D. And I do nothing else than calculating the same calculation with different types. So what happens is you see that a long time, so about 25 or 27 iterations, it looks quite similar. So it's really similar. Then you have a region where it is almost similar, so the results are comparable. But then it happens at one situation, in this case around 27, it happens that the calculations completely go out in a way which cannot be predicted in this way. So we have situations, for example here, or also here, where one iterative propagation comes to an overcrowded petri dish, and another comes to almost completely died out petri dish. So both results are true in numeric, and they only result from this because you use different types. So the suggestion is, okay, always use double precision, but even in double precision you will lose this information. It will happen later, but it will happen. So from this point on, this is now the subtraction of the two results. From this point on, the results are not reliable anymore, and this already happened up after about 25 steps. And this still happen in modern computer systems. So we did some calculations, for example, in moon orbits, and we came to results of about 1 meter after 30 years. So that the orbit is wrong by 1 meter after 30 years if you use the wrong representation. And also what you should learn is, do not mix types. So always use double precision if you want it in a very high accuracy, because in floating point not all numbers can be represented quite well. This is reduced, so the start problem is reduced. But even in modern samples, you will find situations this code is still in use in some laser ranging telescopes, and this is a Fortran code, and Fortran has the situation that, for example, you can identify a double and a single precision, and if you don't do this, the compiler can decide. Nowadays all compilers luckily decide to go to the highest precision, but it was not defined before. So this code might run on different computers in a different way. Another quite interesting thing is that if you use equations which calculate exactly the same, which is just rearranged, will lead to different results in numerics. So if you compare these three calculations, they will, in mathematical terms, they will produce, or they are equal. So they're exactly the same if you watch it in a mathematical domain. For example, here, p to the power, or pn to the power of 2 is the same as pn times pn in math. So if we calculate it in the numeric range, so with this program, and you see that we now use a complete double precision, and we do the calculation here. So these are the three terms, the three equations. And if you calculate this, you'll see that you have the same situation again. So in the beginning, in the first steps here, you have comparable results, and then it starts to become chaotic. So if you do again the subtraction of the results and you watch this, you will see there's a long period, for example here about 50 steps, iteration steps, where it's almost correct. And then it happens that you get not predictable or not usable results. So therefore, I can show you a sample in Matlab code, so which exactly does the same. So we do this calculation and we show how it looks like in a modern computer with a modern program, so Matlab. The code is here. So it's a Matlab program. You see, you have 3 results. Matlab uses double precision, so you should have the best results which a computer can do at the moment, except with double precision. And then we do nothing else than the iteration, 100 steps. And this is the first equation, so this one. This is the second equation, and this is the third equation. So we do iterative processes, and then we plot the results. So let us run the program. So if we run the program, we will get these results, and it looks quite similar to what we saw with the C program. So even in Matlab, in double precision, you have the same situation, so that you get a deterministic behavior if you don't take care on these numerical effects in iterations. So you see that even with modern programming languages, you have to deal with this set of numerical problems. So therefore we need a possibility to deal with this situation. That mathematically equations are exactly the same, and numerically here it's not the same. So we have to take care on what we do if we have iterative processes, and therefore a very important thing is that you should avoid iterative feedbacks. It's not always possible. In most cases it's not possible, and therefore you should do some error calculations and things like that, so that you can identify if there are problems. You should use the highest possible precision. So in best cases double precision or x double or whatever, so that you have the largest precision you can get. But for example, sometimes you can avoid this, and this comes from one of my codes where I calculated satellite orbits as I started here at Octal. And usually you come from the university and you do calculations like this. So you have a starting time, a position of the satellite, and the starting time, and then you calculate the next time by just taking the previous one plus the delta t, so the iteration step. And with this, my orbit did not end up in the real orbit of the satellite. After 5-6 hours, we were completely off target, because with this we have an iterative feedback, and this iterative feedback exactly does the same what you see before. So we lose information, and therefore we get wrong results. In this case, it's quite simple to convert it to a non-iterative process. So in this case, you know how many iterations are already over, so you can calculate n times the delta t, and then you always add it to the original starting time. So you have not so many iterative sets, so you have just an integer times the floating floating point distance, and then you will get the result. So this is much more important and better than this. So always, if you can avoid iterative feedbacks, do it. And another thing is to which I came at a conclusion: if you use external code, which is more or less a black box thing, then you should really think about, do I use it in iterative processes or not? Because a black box, you don't know what happens inside. And especially in modern programming languages, you can use a lot of external code and sources, and you can calculate it in quite a few steps. You come to a result, but the problem is that it might be not numerical correct. So therefore use numerical solutions, which you find in some compendiums like this here, the numerical recipes, so that you have code which is numerical correct, and then you can use this. So the overall conclusion is, think about what you're doing. Not all results are really trustable, just because of maybe errors coming from numerical effects. Deterministic case is just one sample of that. There are more than these situations, and therefore every programmer has to deal with it. And there are really famous samples which show you such situations. One is the maiden flight of the European Ariane rocket, 1996, where a wrong integer type was used, and it resulted to a catastrophic explosion. You will find this code here in the internet, that this is the original Ariane 5 code, but it is just a sample. It was cited several times, but it's not the real Ariane code. It is just a sample, so it's a nice fake. The thing what you should keep in mind is that this caused a lot of money and a long time of stop of rocket launches, just because of this simple small error coming from the numeric conversion between data types. So this is the first lesson. If you have questions, then we'll see each other in the exercise part. I want to say stay safe and see you in the next lesson.